Is the test out? Because I'm having trouble accessing it.
The test is out. The test is available in my math lab. It went live
Oh,
at midnight last night.
okay.
So if you checked before midnight, you wouldn't have seen it, but it's live from midnight, and then it's due on Friday at 11:59 p.m.
All right, thank you.
Two
Speaking of
attempts.
which,
You
oh
do have
yeah,
to go into the test and quiz tab to actually see the test, or bring up all assignments.
Okay, thanks so much.
if I recall, I should have spoken with you
I already
yesterday
took care
about
of
it.
you, Anthony. I already took care of you.
Okay.
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 All right, so we left off, right? We were talking about zeros of polynomials. Hopefully you did some reviewing, remembering how to divide using synthetic division or long division. Also recall that if you divide and you get a remainder of 0, then that means that you have a factor. So the first thing we're going to talk about today is the imaginary zeros theorem, also called the conjugate pairs theorem. It says that if a polynomial p of x has a real coefficient, if a plus bi is a 0, then a minus bi is also a 0 of our polynomial. That is, if a 0 is a complex number, then another 0 is automatically its complex conjugate. Where this theorem comes from, if you think about the times where you've gotten an imaginary or a complex solution, you're solving a quadratic equation and you're ending up with an imaginary number, and an imaginary number happens when we have a negative underneath of a square root. So the two techniques that we use to get that type of answer is quadratic formula or square root property. Okay, those are our only two techniques that have the square root and give us that imaginary number. And you'll notice that both of these techniques have something in common, and that's the plus or minus. So that's why we get a plus and a minus with these imaginary or complex zeros. A plus bi is a 0, then a minus bi is automatically a 0 because of the whole plus or minus in our solving technique. That being said, let's find the zeros of p of x equal to x to the fourth minus 3x to the third plus 6x squared minus 12x plus 8, given that x minus 2i is a factor. This problem is long, don't write big. So they tell us that we have a factor of x minus 2i. Our theorem, however, doesn't tell us anything about factors. Our theorem tells us about zeros. So I want to get the 0 that corresponds with this factor so that I can use my theorem. To go from the factor to the 0, all you do is set the factor equal to 0 and then solve. So that moves over, and we get a 0 of x equals 2i. Our imaginary zeros theorem says if a plus bi is a 0, then a minus bi is also a 0. Well, right now, this 0 is not in that complex form, a plus bi, so I'm going to rewrite it so that it is in that form. And all we're going to do is add a 0 in front. So the a plus bi form of our 0 is 0 plus 2i. Now we can use our theorem to get a second 0. Here's our a plus bi. So by our theorem, a minus bi is also a 0. Well, usually we don't write things 0 minus 2i, so I think I'm going to kind of simplify my 0. So we have a second 0 of x equals negative 2i. And then from that second 0, I can get a second factor. And we get the factor by moving this over and setting it equal to 0. We get a second factor of x plus 2i. What questions do you have on what I've done so far?
No questions.
So is that just the explanation? Is that just an explanation for invert the sign?
Yes, but no, because it can get more complicated. You can end up with factors that look more complex. See, right now, these are zeros that are just imaginary, but you can have factors that look like x plus 1 minus 3i. And when they're more complicated like that, I really encourage you to step it out detailed like this.
Where did you get the 0 in front of the plus 2i?
So I wanted it to look like a plus bi, just so it looked in that form where a is a real number and then bi is an imaginary number. So I don't want to change the value of it. The only thing that I can add to something that doesn't change the value is 0. So it's kind of like I put a 0 placeholder in for the a.
So could a be something else ever?
Sure, but not if you're. So if we had a factor like x minus 1 plus 3i, the 0 would end up being 1 minus 3i. But in that case, we would already know what the a is because we already have a number there. We already have 1. We only plug in this 0 placeholder when our 0 is purely imaginary and not complex. Because like 3i is a purely imaginary number, but 5 plus 3i is a complex number.
Okay.
I mean,
Thank you.
technically an imaginary number is a complex number. Everything is a complex number, but usually when we say complex, we mean that it's looking like this with the 5 plus 3i. Anybody else? Well, our objective is to find the zeros of p of x, and what we did 3 weeks ago to find zeros is we put our polynomial in factored form and then set each factor equal to 0. So that's what we're trying to do here, is we want to get this p of x in fully factored form. Well, we've already found 2 of the factors, x minus 2i and x plus 2i. So I'm going to start factoring p of x. Going to be x minus 2i and x plus 2i, and then there's going to be some other factor. What degree is this other factor going to be?
2.
Degree 2, that's right.
Yeah.
And we know it's going to be degree 2 because each of these are degree 1, and we started with something that was degree 4. So 4 minus 2 1s, we know that it's going to be degree 2. Well, now we have to figure out how to find that other quadratic factor. Let's go back to our number 48 that was so helpful for us at the beginning of this section. So 48, we could rewrite 48 as 2 times 3 times something else. So how would we figure out what the something else is for 48, the third factor?
Multiply 2 times 3 and then divide 40.
Divide.
Right? So we have 2 different options. We could divide 48 by 2 and then by 3, and that would give us our third factor. Or we could multiply these 2 together first and then divide 48 by that. I don't know about you, but I would much prefer to only have to divide once. Plus, you don't know how to divide by something that has an I in it. So what we're going to do is we are going to divide P of X by this product to get the third factor. All right, so let's multiply x minus 2i times x plus 2i. See, when I combine like terms, my middles fall out. I also know that I squared is equal to -1. So we get x squared plus 4. Questions on the multiplying?
No.
But that is not our third factor. That's like the 6 from 48. That is
Do we
now
ex-
what we need to divide our original P of X by to get the third factor. Since what we're about to divide by is quadratic, we will not be able to use synthetic division. We'll have to use long division. And I would definitely put a placeholder in for the linear term in our divisor. Our dividend does not need a placeholder. And we'll divide. X squared goes into x to the 4th. X squared times. We'll multiply x squared by our entire divisor. X to the 4th plus 0x to the 3rd plus 4x squared. Next, we subtract this whole thing where we distribute in our negative, and then we can just add down. -3x to the 3rd plus 2x squared minus 12x. And we do it again. X squared goes into -3x to the 3rd. -3x times. Multiplying back, we get -3x to the 3rd plus 0x squared minus 12x. We'll subtract this whole thing, distributing in our negative. X to the 3rds fall out. Get 2x squared. Now here with our linear terms, we do have -12x plus 12x, which turns out to be just 0. That falls out, but I would be inclined to maintain a placeholder here since it's in the middle of the problem, and then bring down my next term. One more time, x squared goes into 2x squared 2 times. Multiply back, that's 2x squared plus 0x plus 8. We'll just subtract and distribute in our negative. And then when we add down, what do we notice? Everything falls out and we get a remainder of 0. Should we be surprised that we got a remainder of 0?
No.
No,
Why not?
because it was said already given that was a factor.
Exactly, right? What we were doing was finding the third factor. And we had a theorem before that says if it's a factor, it's going to have a remainder of 0. So this right here, x squared minus 3x plus 2, is our third quadratic factor. So I'm going to plug that in there. P of x is equal to x minus 2i, x plus 2i, and then x squared minus 3x plus 2. Our objective is to find all the zeros, so I would see if I could factor this further. Can we factor that x squared minus 3x plus 2?
Yeah.
Yeah, it
Minus one.
factors nicely.
-2.
You got it. X minus 1, x minus 2. Had it not factored, you would have just used quadratic formula to find the solutions, aka the zeros. But now that everything's totally factored, a bunch of linear factors, we can identify the zeros by simply setting each factor equal to 0 and solving. Our first factor gives us a 0 of 2i. Our next one, negative 2i, positive 1, and positive 2. So there we go. Complex zeros theorem says that they always come in pairs. There's always a plus and a minus. Questions at all? All right, well, we've got a couple more theorems to talk about. So far, I've given you something to get started. I've either given you some binomials and said, hey, try this one, or given you a factor to get all the zeros. By the time we're at the end of this section, I'm going to give you nothing but a polynomial and either say factor it completely, or I'm going to set it equal to a number and tell you to solve the equation. So we need to develop some additional tools so that we can do the problem without a jump start. So our next theorem is the fundamental theorem of algebra. Sounds pretty important, doesn't it? The fundamental theorem of algebra says that every polynomial of degree 1 or greater has at least one zero in the complex number system. So I feel like the fundamental theorem of algebra seems trivial to us now, but I mean, it was a huge deal. What this is saying is that every polynomial of degree 1 or greater, so that means that there's a variable, because a constant has degree 0, so x to the first means degree 1. So any polynomial that has a variable in it has at least one zero in the complex number system. This basically tells us that any polynomial equation is going to have a solution. Which again, we've always taken for granted that there was going to be a solution, maybe real, maybe complex, but that was a huge deal for them to actually prove that in math, that we're always guaranteed an answer in the complex number system. Please recall, like I mentioned before, that complex number system includes real numbers, purely imaginary numbers, and then complex numbers. 4, 3i, or 4 plus 3i. Those are our differences. Our N-zeros theorem, this is actually one that we've kind of used before, but not talked about the fact that it was a theorem. This one says that every polynomial of degree n greater than or equal to 1 So again, it's just telling us that there's a variable involved. So every polynomial degree 1 or greater can be expressed as the product of n linear factors. Hence, the polynomial has exactly n zeros, although sometimes the zeros repeat. So we've kind of used this, like I said. With a linear equation, you know you get one solution. With a quadratic equation, you get 2 solutions. With a cubic, you get 3. So whatever the exponent is, that's how many answers we should get. We were using the n zeros theorem when we were doing that kind of stuff in previous math courses. Oh, this one we're kind of just going to take for granted, fundamental theorem of algebra. We just know we're going to get an answer. That means there's no solution here. N zeros theorem, well, that's good to know because whatever the degree of our polynomial is, that's how many answers we're going to get, or that's how many linear factors we're going to get. The rational zeros theorem, this is one that's new for us for sure, and we are going to be using this quite a bit. The rational zero theorem, also sometimes called the rational root test, says that if the polynomial function has integer coefficients, then every rational zero of f of x has the form. You're going to take the factors of the constant term and divide them by the factors of the leading coefficient. Now, you'll see I wrote the words possible rational zeros. We're going to generate a list from all these factors, but not every number on the list will actually be a zero of the function, right? These are possibles. These are ones that we're going to check. Now, it is true that every rational zero of the polynomial will be on this list, but the list is much larger than the actual zeros. We're going to use trial and error to test these possible rational zeros to find the actual zero. I just want to remind us what the word rational means. In math, the word rational means that it can be rewritten as a fraction. So this list of possible rational zeros really only gives us the nicest of all the zeros. It doesn't include any of our irrational numbers, which are numbers that might have a square root in it. These are not our non-repeating decimals, things like that. So this list is really just giving us either whole numbers or fractions for us to test. So let's see how we use this theorem. We want to list the possible rational zeros for p of x equals 6x to the third plus x squared plus 5x minus 2. Our possible rational zeros. It's going to be this fraction. It's going to be a weird list. So we want the factors of the constant, and then we're going to divide those numbers by the factors of the leading coefficient. So what are the factors of our constant -2?
So -1, 2.
Right, 1 and 2, that's how we get 2. But it's a -2, so we could have a -1 times a +2, or a +1 times a -2. So the factors are actually plus or minus 1 and plus or minus 2. Now we want to divide this by the factors of the leading coefficient. And our leading coefficient is 6. So what are all the factors of 6?
1 and 6 and 2 and 3.
1
Positive
and
or
6 and 2 and 3. But just like the factors for our constant, to get a +6, we could do a +1 times a +6 or a -1 times a -6. So when we list out the factors, we need to say plus or minus for each one of them. And that's going to just be true generally across the board. Anytime you do this, everything's going to be a plus or minus. So actually what I usually do is I'll actually write it like this. I'll just put plus or minus and then put a parenthesis so I don't have to write the plus or minus over and over again. Some of these numbers have a ton of factors, and I don't want to write plus or minus every time, so I usually write it like that. So now we want to clean up this list because I look at that, I'm like, what am I supposed to do with this? Well, the first thing I want to address is the plus or minuses. If you take a plus or minus and divide it by a plus or minus, you actually get a plus or minus. And just to show you why we get that, if I choose the two positives and divide, I'm going to get a positive. If I choose the two negatives and divide, I'm going to get a positive. If I choose the positive from the top and the negative from the bottom, I'm going to get a negative. Or if I choose the negative from the top and the positive from the bottom, I'm going to get a negative. So when we divide a plus or minus by a plus or minus, we get a plus or minus. And I usually write PRZ because possible rational zero is a lot to write. So every single one of our answers, it's going to be plus or minus. So I write a plus or minus before and then a big old parenthesis. Now we want to do every possible combination of numbers from the numerator with numbers from the denominator. I try to do it as systematically as I can so that I don't miss anything. So I kind of think of it like distributing. I'll start with like 1 in the numerator, and then I'll take it over each number in the denominator. So 1 over 1 is 1. 1 over 2, a half. 1 over 3, a third. 1 over 6, a sixth. And then I'll move on and do the same thing with the 2. So I'll take the 2 with each number in the denominator. 2 over 1 is 2. 2 over 2 is 1, which is already on my list, so I don't need to repeat it. 2 over 3 is 2/3, and then 2 over 6 is 1/3, already on my list, so I don't need to repeat it. This is our list of possible rational zeros. So clearly, not every one of these numbers is going to work. Our n-zeros theorem tells us that the number of zeros we have is equal to the degree. And the degree of this polynomial is 3, yet I have 12 numbers in my list of possible rational zeros. So clearly, they're not all going to work. And the way we would check, which is what we're going to do in subsequent examples, the way that we start checking to see which of these possible rational zeros are actual zeros is just by dividing and dividing and dividing and seeing whether or not we get a remainder of 0. You may look at this list and say, Allison, oh my God, 12 numbers, that's so much. But we just narrowed it down from infinity to 12. So I think that that's a pretty concise list, considering we had an infinite number of numbers just a moment ago. Questions on listing out our possible rational zeros? This is going to be like your first step on a lot of these problems, because this is what we're going to use to get started.
I have a question.
Yep.
So like, I don't get why we only use the 6 to like divide.
That's the rule. I mean,
Okay.
I would have to prepare the proof of the rational zeros theorem. I don't have that offhand anymore.
Yeah.
Did at one point. I hate to say because I said so, but that's the theorem. Again, there's a real complicated proof. This is actually also why the AC method for factoring trinomials with the leading coefficient other than 1, it actually comes from the same thing. It's called the Eisenstein criterion that both of those theorems come from.
Primero veamos las amenazas.
But I don't have a full proof ready to go offhand.
I just didn't know if there was like a reason.
Yes, there is. But one that is far beyond the scope of this course.
Yeah.
So we're going to just remember the theorem. Anybody else?
If the leading coefficient is 1, would we just skip the division part?
Well, I mean, yes,
it would
but
all be
no, I'm going to
divided by
write
1.
it. I'm going to write it, but of course, dividing by 1 doesn't have an effect. We're going to see ones that are like that. But yeah, Anthony. All right, so see, Anthony, this next one, leading coefficient of 1. It's like I could read your mind. So here we're going to find all the zeros of this polynomial f of x. We're going to start by finding our list of possible rational zeros, and then we're going to test them using division to help us factor this. We don't have to test every single number. We just have to test enough numbers until we can get it in factored form so we can answer the question. Our list of possible rational zeros. We're going to take the factors of the constant and divide it by the factors of the leading coefficient. We know that everything's going to be a plus or minus. So let's start with the factors of our constant, 12. So what are the factors of 12?
1, 12, 2, 6, 3, 4, all plus or minus.
There we go. And I don't care how you write it. Some people really like to write it in increasing order. Some people aren't as comfortable with that and kind of write the pairs 1, 12, 2, 6, 3, 4. That's fine. And then we're going to divide it by the factors of our leading coefficient. Our leading coefficient is 1, so that's the only factor. We know that a plus or minus divided by a plus or minus is equal to a plus or minus. And since the only number in the denominator is 1, like Anthony was mentioning, if we divide all those numerator numbers by 1, we just get all those numerator numbers. Oh, there is our list of possible rational zeros. This is what we're going to use to get started. These are the numbers we're going to start checking.
One.
And it kind of is just trial and error. You just got to pick one and try it and see if it works. So what number would you like to start with?
1.
1. No placeholders are necessary. Can you guys hear my kids?
Every once in a while, but no.
Okay, well, I know I can hear Layla's kids, but I'm just wondering if you can hear my kids because I keep going in there and telling them to be quiet. All right. So we perform our synthetic division and super happy, remainder of 0. And I'm happy about that because that tells me that I have a 0. And if I have a 0, that means that I have a factor and I can start breaking down f of x. All right, so if our 0 is positive 1, what's the factor that goes with that?
X minus 1.
X minus 1. It's always the opposite. And then we want our next factor, and that next factor is the quotient from our division.
Okay, x squared.
It's going to be quadratic because we had a third degree and divided it by a first degree. That's x squared minus x minus 12. Once you get down to a quadratic as your biggest factor that you have left, you can stop testing the zeros because we have all kinds of other methods for solving quadratics. We can either try to factor it using some of our other traditional methods, or we can always use quadratic formula to find the zero. But this one factors nicely. X squared minus x minus 12 turns into x minus 4 times x plus 3. And once we're in factored form, we can identify all of our zeros by simply setting each factor equal to 0 and solving. Oh, we get 3 zeros, which we shouldn't be surprised by because we were degree 3 and our n zeros theorem told us we should have 3. Those 3 zeros are 1, 4, and negative 3. Questions? All right. Well, sometimes our list of possible rational zeros can be large. These two examples we've done thus far have only been like 12, but I mean, you could have coefficients of 48 and 144. You could end up with lists of possible rational zeros that have tons of numbers. Now, of course, I'm not going to do that to you. I would stay probably 20 and under, but you could have these huge lists. But even with a list of 20 or 12, it'd be nice to narrow down the list. So we have a couple techniques to help us make more educated choices about which possible rational zeros to test. Our first technique is called Descartes' rule of signs. And Descartes' rule of signs says if a polynomial function has real coefficients and the constant term is not 0, then the number of positive real zeros of the polynomial is either equal to the number of sign variations in p of x or less than that by a multiple of 2. The number of negative real zeros in a polynomial is either equal to the number of sign variations in p of negative x or less than that by a multiple of 2. So let me translate. So we have these zeros, and we could either have real zeros or we're going to have complex zeros, right? I mean, that's kind of our options with numbers. Either they're real or they're imaginary. So we're either going to have real numbers or we're going to have complex numbers. And then the real numbers can be broken down into either positives or negatives. So we're going to be looking at these zeros.
Everyone mute themselves, please.
Layla, can you mute your mic, please? Thank you, dear.
Yes.
Yeah, just unmute yourself when you want to talk, but let's keep it muted in the meantime because we all have all our family home.
I took them out, sorry.
It's okay. We're all in the same situation.
Yeah.
Okay, so we could either have positive real zeros, negative real zeros, or complex zeros. And Descartes' rule of signs only talks to... Now it's my kids. Hey, quiet in there. So Descartes' rule of signs only talk about the real zeros, the positive real zeros and the negative real zeros. So the number of positive real zeros is either equal to the number of sign variations. And that just means how many times it turns from plus to minus or minus to plus. It's either equal to that or less than that by a multiple of 2. And for the negative real zeros, we're going to look at the number of sign variations that happens in P of negative x. So we'll actually have to plug negative x in for x, clean it up, and then have a new function to look at. The number of negative real zeros is either equal to the number of those sign variations or less than that by a multiple of 2. You'll notice that both of them say or less than that by a multiple of 2. What's going to happen is we're going to create a chart, and we're going to come up with different options. In the first theorem of the day today, our complex zeros theorem, we saw that complex zeros always come in pairs, a plus bi and a minus bi. So we're going to be subtracting out the possibility of complex zeros. And since complex zeros always come in pairs, we're going to be subtracting by multiples of 2. So we want to determine the number of possible combinations of zeros for P of x equal to x to the 4th plus 2x to the 3rd plus x squared plus 8x minus 12. Hold on, I'm going to send my kids in the other room. I feel like they're loud. Dude, hey, you got to go in the back. Yeah, you're parked out. Now, just either downstairs or back in the bedroom. Move it. Okay, so like I said, we're going to make ourselves a little chart. Positive real zeros, negative real zeros, and then complex zeros. The first part of our theorem deals with the positive real zeros. It says that the number of positive real zeros is equal to the number of sign changes in our polynomial or less than that by a multiple of 2. So let's count the number of sign changes in our polynomial. Plus, 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 minus. So the only time it switches is here at the very end. So the number of sign variations is 1. And I'm not going to fill out the chart yet. I'm going to put my options up above kind of the heading. So the number of sign variations is 1. Our theorems, or our rule says that it could be less than that by a multiple of 2. We're talking about a quantity of zeros, not like what the zero actually is, what number it is. We're talking about a quantity. So when we talk about quantities, we don't talk about quantities in terms of negative number. I've never looked in the refrigerator and gone, oh my gosh, I got -2 gallons of milk. Right? Quantities we talk about either as a positive number or 0. I might say, oh, I don't have any eggs. So 0 makes sense for a quantity, positive numbers make sense for a quantity, but negative numbers don't. So if I take this 1 and I subtract 2, which is my first multiple of 2, I get -1. And as we just said, a negative number does not make sense when talking about a quantity. So there is not a second option possible for positive real zeros. There is going to be exactly 1. Now we want to move on and do the same kind of thing for negative real zeros. Our rule says we need to take a look at P of negative x and count its sign changes to make some decisions about negative real zeros. So we'll start by plugging in negative x. and then we want to clean it up. Any negative raised to an even power turns positive. Any negative raised to an odd power turns negative. This is x to the fourth. Here we're going to have negative x to the third is negative times this positive 2. This is going to be minus 2x to the third. Squaring a negative makes it positive, plus a positive. Minus 8x minus 12. And now we want to count the number of sign variations, how many times we switch from plus to minus or minus to plus. Here's from plus to minus, minus to plus, plus to minus, and then minus minus stays the same. So here, p of negative x, we have 3 sign changes. That is going to be our first option for negative real zeros. Next, we want to lessen that by a multiple of 2, so we just are subtracting 2's. If I subtract 2 from 3, I get 1. Oh, we said that any quantity that was a positive number or 0 made sense. So a second option of positive 1 makes sense. If I subtract 2 a second time, I get negative 1. Negative 1 does not make sense for an option for a quantity. So I'm going to end up with 2 options for negative real zeros and 1 option for positive real zeros. And now I'm ready to fill in my chart. Questions on our options?
Where's the one coming from?
The second one,
Yeah.
we subtract 2 from 3. Because our rule says or less than that by a multiple of 2, so we're subtracting 2. And as long as you don't get a negative number, it's a viable option.
And then
Okay.
where'd the positive one, like on the positive side, where'd that one come from?
That was from the number of sign changes in p of x. Only one time did we switch from plus to minus or minus to plus.
So do the sign changes actually give us factors of the equation?
No, they're just, you'll see. Give me just a minute. You'll see. And then where the 3 came from was just that's how many times we changed from plus to minus or minus to plus when we looked at p of negative x. Now we're going to be ready to fill in our chart, and we're actually going to start with the first 2 rows only, the real stuff. We need to do every possible combination of our positive real and negative real. So to me, it looks like distributing. I'm going to do 1 with 3 and then 1 with 1. So I'm going to do 1 with 3 and then 1 with 1. Next, we need to fill in the complex column. Since our polynomial is degree 4, we know that we're going to have 4 zeros. Each row must add across to be the degree. We basically need to figure out what number would have to be in the complex column so that each row adds up to be 4 in this case. Our first row, we already have 1 and 3, so what do we add to that to make 4? 0. In our second row, we have one positive and one negative real. So what do we need to add to those two ones to make 4? 2. And there's our chart. I know you're thinking, so what? What does it tell me? Oh, what I look for when I'm looking at this chart is the first thing I'm doing is I'm looking for zeros in my first 2 columns. I'm really only paying attention to the first 2 columns because we're testing possible rational zeros, and rational zeros are real numbers. So I'm only looking at the real column. The first thing I'm doing is I'm looking to see if there are any zeros in my 2 real columns. If there are, I avoid that type of number. So if like this had been a 0 here, that means that in one option I have negative real zeros, but in the other option I don't. So I would avoid checking negative numbers because it's a 50-50 chance that there aren't any. While if I look at the positive real column, there aren't any zeros, so that means that I'm guaranteed to have a positive answer. So I would start by looking for the column that has zeros in it, and then I would avoid that column. In this example, we don't have any columns with zeros. So, and again, I'm only looking at the first 2. So I would choose the type of number that had the biggest numbers in their column. So since 3 is the biggest number and it's in the negative real column, I would start with my list of possible rational zeros checking negative numbers. So that's the first thing that we can use to help us narrow down the list and make good choices. The next is our lower and upper bound rules. Descartes' rule of signs we typically do before we start checking zeros. This upper and lower bound rules that we're going to talk about, we don't apply this until we're actually in it, doing all the division, checking for the zeros. So if we have some polynomial with a positive leading coefficient, and we're dividing f of x by x minus c using synthetic division. So this only works when we're doing synthetic division. If c is positive, so that means the number in the box is positive. If c is positive and each number in the last row is either positive or 0, then c is an upper bound for the real zeros of f. So that means, like, if you're doing synthetic division and you got a positive number out here, if you get all positives or a 0 in your bottom row when you're doing the synthetic division, then that means that you don't want to check numbers bigger than 3. 3 is an upper bound. So check numbers smaller than 3. The second part of this deals with when c is negative. Excuse me. If c is less than 0 and the numbers in the last row alternate between positive and negative, 0 could count as either, then c is a lower bound for the real zeros of f, and you should check a number bigger than that. So if we're dividing by -4, and we end up getting something that alternates between positive and negative numbers, that means that -4 is a lower bound and we should check a number bigger than that. Honestly, neither one of these are must-dos. It just makes the checking of the possible rational zeros easier. Shorten it up. Rather than checking all 20 numbers, maybe I only had to check 5 numbers. So let's put all this together into one problem. So given that p of x is equal to 2x to the fifth minus 5x to the fourth minus 5x to the third plus 25x squared minus 7x minus 10, the first thing I want you to do is make our chart. We're going to use Descartes' rule of signs to determine possible combinations of positive real zeros, negative real zeros, and imaginary zeros. Then we're going to use our rational zero test to determine our possible rational zeros. And then in part C, we're going to test those possible rational zeros and rewrite our polynomial function as a product of linear factors. And our n zeros theorem tells us that we're going to end up with 5 linear factors here because we are degree 5. So we'll start with our chart. We have our positive real column, our negative real column, and our complex column. We start by determining our options. For positive real zeros, our max option is going to be the number of sign changes that we have in our p of x. So let's see how many times it switches from positive to negative. It's once, twice, 3 times. The maximum number of positive real zeros we could have is 3. But Descartes' rule of signs says it could be that number or less than that by a multiple of 2. So I'm going to subtract 2 from 3. I get 1. 1's not negative, so that's a second option. I subtract 2 a second time. That's going to give me -1. It does not make sense to talk about quantities in terms of negative numbers, so that's not a viable option. Those are my only 2. We're going to do the same thing for negatives, but we need p of negative x. And we're going to look at the number of sign changes in p of negative x. All right, then we're gonna clean it up. So a negative raised to the fifth is negative times a positive 2, that's gonna be negative. Negative raised to the fourth is positive times a negative, it's gonna be negative. A negative raised to the third is negative times a negative is gonna be positive. Negative squared is going to be positive times a positive stays positive. Negative times a negative is positive. And then minus 10. So there is kind of a shortcut if you want to finding your p of negative x. Because of this whole even odd rule, raising a negative to either an even or an odd power, all you need to do is change the sign on the odd degreed terms. The even degreed terms stay the same, the odd degreed terms switch, and that gives you p of negative x if you're interested in a shortcut.
I think the wireless earbuds would be useful for this, aren't they?
They're right there in the little charging pod.
Okay. Oh, so
You have to turn the Bluetooth back on.
Anthony, you need to mute your mic, dear.
oh, sorry. My mistake.
All right, so now we want to count again how many times we're switching between positive and negative with p of negative x. So there's 1, 2. I guess that's it, just 2. So our first option, our maximum number of negative real zeros would be 2. And then we're going to do the whole subtract 2 thing. So if I subtract 2 from 2, I get 0. As long as you don't get a negative number, it's a viable option. Sometimes we say, oh man, I didn't bring a pencil to class. I don't have any pencils. So 0 makes sense when we're talking about a quantity, just not a negative. If we subtract 2 a second time, we get negative 2. That does not make sense when we're talking about quantity, so this is it. We have 2 options for positive, 2 options for negative. Now we want to fill in our table doing every possible combination. So I'm going to do 3 with 2, 3 with 0. Then I'm going to do 1 with 2 and 1 with 0. So we're actually going to have 4 rows this time. So 3 with 2, 3 with 0. 1 with 2, 1 with 0. Now we're going to fill in our complex column because we know that each one of these rows have to add up to be our degree. And our degree is 5. So we just got to figure out what number goes in our complex column so that everybody adds up to be 5. So we already have 3 and 2, so 0. And our next option is 3 and 0, so this has to be a 2. 1 and 2, we need another 2 to make 5. And then in our last row, we need this to be 4 so that it adds up to be 5. I always double check when I make my chart that all the numbers in my complex column should be even numbers, since complex zeros come in pairs, in twos. Multiples of 2s are always even numbers, so I always double check that. So what does this chart tell me? Well, I'm looking at the first 2 columns and I see these zeros right here. That tells me it's a 50-50 chance that there are no negative zeros. Whereas if I look in my positive column, I have a number for every single one of those, a positive number. So I'm guaranteed at least one positive real zero, 100% chance of positive. So if it was me, when I get my list of possible rational zeros, I'm going to start by checking positive numbers. Because I like the for sure bet, not the 50-50 bet. In part B, we want to list out all of our possible rational zeros. We take the factors of our constant and divide it by the factors of our leading coefficient. So first we start with the factors of 10. 1, 2, 5, and 10. And then we divide that by the factors of our leading coefficient, only factors of 2 or 1 and 2. And then we want to clean up this list. We know that a plus or minus divided by a plus or minus results in a plus or minus. And now we want to do every possible combination. So I'm going to take each one of these numbers over 1, and then I'm going to take each one of these numbers over 2. All right, so each one of those numbers over 1, when we divide by 1, we just get those same numbers back. And now we'll take each one of these numbers over 2. 1 over 2 is a half. 2 over 2 is 1, which is already on our list. 5 over 2 is 5 halves. And then 10 over 2 is 5, already on our list. So there we go. There's our list of possible rational zeros. Questions so far? I know, I'm sorry. I'm going to run over. I probably need like 8 or 10 more minutes to finish this problem. So if you have to go, that's fine. I'm recording this and I will post the recording. Now it's time to start checking these possible rational zeros. Long time ago, when we first started this section, we talked about a theorem called the remainder theorem. And the remainder theorem says that if you just plug the 0 into the polynomial, it tells you whether or not that's a 0. Right? We saw it here. That when I divided by x minus 2, if I plug 2 in, it's going to give me the same remainder I would get if I actually did the division. When I'm doing these longer problems, I do actually use remainder theorem, but only a little bit. I use remainder theorem to check +1 or -1. And I use it because it's easy. See, if we use remainder theorem, if we plug in 1 for x, 1 raised to any power is just 1. So the variable portion becomes 1. We multiply it by the coefficient. We're left with the coefficients. So to check +1, all you need to do is add up the coefficients of your p of x. If you get 0, then you know that you're going to have a 0, and as a result of having a 0, you're going to end up with a factor. So let's add that up. 2 plus -5 plus -5 plus 25 minus 7 minus 10. If we add all those up, let's see what we get here. -10, -7, -5, -5. So that's a minus 27. And then there's a positive 27. So if I add all that together, I get 0. That tells me that +1 is for sure going to be a 0. So I'm going to divide that one first. And you don't have to do that. You can just start checking your list. You don't have to do that. I just think it's an easy, quick check. And we divide. We get a remainder of 0, which we're anticipating because we already knew from remainder theorem that 1 was a 0. Now we can start factoring our p of x. Since +1 is a 0, what's the factor going to be?
X minus 1.
X minus 1. And then our next factor is going to be what degree? Fourth degree, because we had a fifth degree. We divided it by a first degree. We're going to be left with a fourth degree. And down here are the numbers for that quotient. 2x to the fourth minus 3x to the third minus 8x squared plus 17x plus 10. And now we're ready to check another number. You can easily check -1 by adding up the coefficients of p of negative x. So if we add up these coefficients, that 37 minus 17, that's a positive 20. So I don't get 0, so I know right away that -1 doesn't work, so I'm not going to bother dividing it. All right, so let's choose another number. What do you want to use? Well, then I'll just pick, let's try 2. And remember, we're now dividing it into the 4th degree because we're trying to break down that polynomial, so you don't want to go back to the original. Oh man, this one was so close, but didn't work out. And we got a remainder of 20. That's not 0, so that means that this doesn't work. I don't know about you, when I see that 10 and 10, I'm like, man, it's so close. Maybe -2 is going to work. So even though my chart inspired me to start with the positives, that doesn't mean that you have to stay with the positives. So this right here, this is so close, I'm going to switch to -2 because that almost worked.
I have a question then when you're finished.
Yep,
too.
go ahead.
So when we're checking those numbers that we listed, you're checking the positive and the negatives?
Yeah. The only way I wouldn't check both is say that my negative column was all zeros. Well, then I wouldn't waste my time checking any of the negatives because my chart tells me none of them are going to work.
Okay.
So unless
you.
that's the case, or we're doing an application problem where a negative number wouldn't make sense, other than that, I'm checking both.
Okay, thank you.
So yay, -2 worked. We got a remainder of 0, so I'm going to continue factoring my p of x. X minus 1 is my first factor. I got a 0 of -2, so what's that factor going to be? X plus 2. And then our next factor is going to be cubic. 2x to the 3rd minus 7x squared plus 6x plus 5. As soon as I get to a 4 terms, I'm totally going to try to factor by grouping, because the factoring methods that we already know is a whole lot easier than doing all this division stuff. So I would check to see if I could do factor by grouping. Unfortunately, I can't in this example, but it's worth a shot. I'm going to be happy the time that it does work out. All right, well, notice that so far we got 1 positive and 1 negative. If we go back to our chart, since we have a negative, we know that these 2 options are not options. So our chart is telling us that we're guaranteed a second negative number. So I would be inclined to check another negative number. And for the sake of time, let's check -1/2. We get a remainder of 0. So I know that -1/2 has to be a 0, and it's going to give us another factor. The 0 is -1/2, so the factor is going to be x plus 1/2. And we're going to end up with a quadratic, 2x squared minus 8x plus 10. Once you get down to a quadratic, you do not have to check any more zeros by division. We're going to be able to finish up the problem using other techniques that we already know. We're either going to be able to factor it, or if it doesn't factor, we'll be able to use quadratic formula to solve and then work backwards to the factor. Right away, I see that this quadratic has a GCF of 2, so I'm going to factor that out. Leaves us with x squared minus 4x plus 5. When I think of two numbers that multiply together to be a positive 5, but add together to be a negative 4, nothing works. So we are going to use quadratic formula to find the zeros. And then get the factors. So here it goes. X equals negative 4 plus or minus the square root of negative 4 squared minus 4 times 1 times 5 all over 2 times 1. So that's 4 plus or minus the square root of 16 minus 20 over 2. 4 plus or minus the square root of negative 4 all over 2, which is 4 plus or minus 2i all over 2. That's 4 over 2 plus or minus 2i over 2. Which is 2 plus or minus I. And now that we have these two complex zeros, we can get the factors. The easiest way I think to do that is rewrite each of these as x equals. So x equals 2 plus I, and then x equals 2 minus I. To go from the 0 to the factor, we just move everything over to the same side as the x. Oh, that's going to be x minus 2 minus I and x minus 2 plus I. Now we're almost done. Now the last thing we need to do is rewrite our p of x fully factored. P of x is equal to 2 times x minus 1 times x plus 2 times x plus a half times x minus 2 minus I times x minus 2 plus I. And there we go. No, that was intense, but you should feel like fulfilled today. That was awesome. What questions do you have?
What would be our homework today?
I'm not answering that question yet. What question on this do you have?
For the x equals 2 plus I and x equals 2 minus I,
Yes.
we want to take all the factors and like set it equal to 0 basically.
Yes. To
Okay.
go from the 0 to the factor, you just set it equal to 0. So I mean, I guess
Okay.
technically. Let me get that.
Okay.
I know it's a lot. We're going to do more next week, but I would also encourage you maybe to rewatch the videos. And this problem had like absolutely everything in it. I usually don't put absolutely everything in one problem. Anybody else? Questions on this? Okay, to answer Anthony's question, the most important thing that you should be doing today is finishing your test, right? Get online and do that test. Also, I don't know why it's just you. What happened there? So get your test done. That's got to be your priority. It closes on Friday at midnight. But then just, you know, you can start working on your homework. It's not due for a while. I think we talked last time that it wasn't due until April sometime. So, you know, you can slowly start working on your MyMathLab, slowly start working on your take-home quiz, but your test really should be the priority. You would be short-sighted if you did not take advantage of both attempts at that exam. Do the first one for sure, see how it goes. You can review the test, but only immediately after you submit it. After that, you will not be able to view it. So take it, review it, and then prepare again and take it a second time. The questions are pooled. I spent hours making that test, so it's not just going to regurgitate exactly the same test. I've pooled different questions together, so take it, review it, and I would definitely take it again.
So it's going to tell us our final grade at the
Yep,
end?
but not until you submit the whole thing. Just like the other quizzes, you got to complete the whole thing. It's not going to answer question by question whether you got it wrong. So you're going to do the whole thing. I think it's 20 questions. Hit submit. It's going to give you a grade, and then you can only see your answer and the correct answer immediately after submitting. So don't hurry up and X out, because that's just going to be it then.
Okay, thank you.
Anybody else?
Yeah, the second attempt, it will be like I can do same day or the second day?
You can do it any day as long as you get it done before the second attempt. All attempts have to be finished before Friday at 11:59 p.m.
Yeah, okay, I can do it like today and tomorrow I can do the second
Absolutely. You can do today and tomorrow, today and Friday.
attempt.
Yep.
Okay.
Anybody else? Okay, have a wonderful day and weekend. Get that office hours survey done. If you haven't, I will email out the decision for office hours. I gave everybody to the end of today to get it submitted. So tomorrow I'll make that decision and get that sent out. And I will also post this recording somewhere. I'll send you guys an email and let you know.
Okay, same to you.
Have a great day.
All right. Thank you.
Same to you. Thank you.
Thank you.
Have a good day.